Thank you. Let's see. Okay. So here you can think of a simplicial set as a sequence of sets labeled by natural numbers together with simplicial structure. Those are maps between the sets at level n and n-1. So these are phase maps denoted by di and the degeneracy maps denoted by sj. And the idea here is that the simplex category delta can be generated by the so-called cophase maps and codegeneracy maps that relate the object n to n-1 in this case, and the object n and n+1 in this case. So the morphisms, the dual morphisms, they would go in the opposite direction. So it's n-1 to n, so that would be a cophase map. That's a morphism in this category delta. And the co-degeneracy maps would go from n+1 to n. And these morphisms, they generate all the morphisms here in delta. So I'm not going to write out what these morphisms are specifically. So these are just set maps of a certain form. But I would like to go to an example. So that is the example that we will use. Is there a problem with the connection? Is anyone trying to talk? Hello, can you hear me?
I think it's fine.
Okay, it's fine. Just I heard some background noise. I thought like there's something going on. Okay, so let's consider a group G. So it's a topological group. So we define the classifying space of this group denoted by BG. This is the geometric realization of the simplicial set, which I will simply denote by g to power n. So this is the n-fold direct product of this group by itself, n times, and n goes over the natural numbers. The simplicial structure here, I'll just explicitly write these maps in this case, since this is the case of interest. So the n-tuple in level n is going to be mapped under the phase map di to g2, gn when I is equal to 0, and to the tuple g1, gi times gi plus 1, gn when I is between 0 and n. But finally, in the last case, it will be mapped to g1, to gn-1 when I is equal to n. So in the first and the last case, you omit the first and the last element, and in the middle, you just multiply the consecutive two elements using group structure. And degeneracy maps, they go from g1, gn to an n+1 tuple. So the tuple will look like g1, gj. So we go to the jth one and insert the 1 afterwards, and then gj plus 1, gn. So this is the identity element in G. So essentially, the phase and the degeneracy maps use the multiplication structure of the group and the identity element in the group.
Yo, bro.
Okay, so I hear some background noise. If you can just mute your microphone, that would be great. So the idea here is that the one thing that's not defined is the geometric realization. So this is this can be thought of actually obtaining a geometric object, a topological space out of this combinatorial data. And I'm not going to define what this is precisely, but the way you should think of it as like a construction that goes from starting from a point, which is the zero simplices, that will be 0 to g to power 0, just a single point. And then you go to the one simplices, that will be an edge for each group element G. So these are one simplices. Two simplices are denoted by pair of group elements. So this is like a triangle. So it's a 2 simplex, 1 simplex, 0 simplex. And the third level would be a triple of group elements. So it's a tetrahedron. So 3 simplex. So this, the edges here are denoted by these triple of group elements, and then so on. So you can you do this, you consider all of these higher dimensional simplices as well. And the idea is that the geometric realization tells you how to glue these pieces to the previous stage. So you just start from a point, you glue these two endpoints to this point to obtain, so at this point you obtain like a bouquet of circles. And then in the next stage, you glue these triangles by identifying the labels with the corresponding circles. So the third one here is always determined to be the product, G1 times G2. And so on. You just continue this gluing process, which is determined by these phase and degeneracy maps. And this is, at the end, you obtain a space, and that space is the classifying space BT. So this is a topological space. Okay, so our goal is to, well, there's one thing I didn't say, is that we are talking about simplicial sets, but essentially we are talking about simplicial spaces here, because these GNs are in fact topological spaces. So each n simplex is a space. It's a space of n simplices given by g to the power n. So it has the natural topology coming from the group. Okay, so let's go to the next stage here. The idea here is to modify the classifying space construction. So it's the modification to this construction. I introduced the classifying space as an example, but it is actually the example that we will consider in this talk. So it's kind of the main construction. The modification is introduced by Adem-Cohen-Torres Giese. The idea is to restrict the space of cells, n cells, to something smaller. And the construction is it belongs to a family of constructions, but the one I'm interested in this talk is denoted by bz mod d, g. So the construction depends on the object here, integers mod d. So this is the notation. This space is the geometric realization of the simplicial space, which takes the object n to the space of homomorphisms from z mod d. So this is the ring of integers, as I said, n-fold product to G. These are group homomorphisms topologized as a subspace of G to the power n. As you see, that's not, the space of simplices is restricted. So now this is smaller. An element here would be an n-tuple of group elements such that each element to the power d is the identity and they pairwise commute. So this I refer to as a d-torsion condition. Okay. So at the end, using the same phase and degeneracy maps, we obtain a space, which is this space over here. We can replace z mod d with z. And in this case, we obtain the classifying space for commutativity. So this is, so this space is studied more intensely. This is rather kind of new, and we will look at this in this talk. Here, you drop the last condition of being d-torsion to obtain this space. So you're looking at n-tuples of pairwise commuting group elements. More generally, we can construct this similar space, if you take a cosimplicial group from, so that would be a functor from the simplex category to groups. If you start with a functor like this, you can also define a classifying space, a space corresponding to these functors by similarly modifying this. So the shortcut notation for this would be this. So that means you look at the homomorphisms from the nth level of this functor to the group G, and then you take the geometric realization. And it turns out that, so the fact here is that the space constructed this way, or this one in particular, is a classifying space. For principal G bundles with tau structure, with gamma structure. So this is a new notion of principal bundle. So the gamma structure, whatever the gamma here, is going to put some restrictions on the transition functions. That's kind of the principal bundle we are talking about here. So what they are precisely are is not important, but the idea is that this construction is a modification, but at the end you obtain a classifying space as well. So these are classifying spaces for these certain types of principal bundles. So the goal here in this talk, or in general, for this type of question, for these classifying spaces, the general idea is to understand the homotopy type of this space. And we will restrict most of the time to the unitary group of M by M matrices.
Cihan, bir şey sorabilir miyim?
Yes.
On this definition of ZDG, what happens when you have n equals 0?
Sorry, where precisely you said inside CDG?
When you define classifying space.
Right here?
Yeah. So what happens when you have n equals 0?
Oh, so n equals 0 is just a singleton. So this is regarded as the trivial group. So, okay.
So on the gamma also you have to make the assumptions like that? Is that?
Essentially, yes. So most of the time when we look at these kind of constructions, we take gamma 0 to be the trivial group. Yes. Yes.
So no other assumption, just that will be okay.
No other assumption. I might be a little bit overgeneralizing here. But probably, so you might need gamma 0 to be 1 to be able to say something sensible about the homotopy type. But the correspondence here about the fact here, like the correspondence is, in principle, is supposed to work without any condition.
Do you assume inclusion, like monomorphisms? The gamma takes maps to monomorphisms in groups or things like that?
Yeah, so the best assumption, which is, I mean, if you want to say something about this construction, you should most likely have this condition, which is this one. Whatever you put here is supposed to be regarded as a subspace of that, so that you can relate it to the normal ordinary classifying space and to be able to say something sensible about the homotopy type. This is the kind of the usual assumption here. Yeah, the idea is to think of gamma as introducing extra algebraic relations on these n tuples. That's the idea. To be able to say, to be able to have some control on the space. It cannot be super general. But I don't want to go into that, because for us, this will be the only construction that we are interested in, and maybe this one just to make some comments on. Okay, so in this talk, we're essentially interested in the unitary group when G is equal to the unitary group. But the problem is that it's kind of hard to compute the homotopy groups of this in general. So could you unmute yourself? Someone, I hear some background noise. If you haven't unmuted yourself, please unmute yourself. Okay, so we will look at the unitary group. We cannot look at the unitary group because the homotopy groups are complicated. What we will do is to do a trick, which is the stabilization. So this is like a very standard trick that one considers in algebraic topology. So you look at the sequence of maps between the unitary groups, which takes a unitary matrix to the unitary matrix given by this. So you just add a 1 on the diagonal and zeros otherwise. So you consider this sequence of groups, and then you take the union of this, or the colimit, to obtain a group, which is the stable unitary group. So the dimension disappears, so you just have U. These maps induce maps between the construction here, the classifying spaces, and in particular, or also in between these modified constructions. So you have a map from this to the next stage, UN+1, and you take the colimit of these to obtain BZ mod D, U. So this is the definition of this space. You take the colimit of these pieces. And here in this talk, we will study this. Whether this stable space. And at this point, we don't know what this space is. Is it like simpler than the previous ones? Well, most likely yes, because it's what happens if you just drop Z mod D and just comes to the classifying spaces. You would get BU over here. So this is a subspace of BU. And remember that BU is an infinite loop space, and it represents topological K theory, complex K theory. And we will obtain a similar result for this one, for this space, and there we will see the corresponding generalized cohomology theory, and we will see that it's an infinite loop space. The corresponding generalized cohomology theory will be called the commutative d-torsion K theory. So it's the pairwise commuting is commutative, and the d-torsion. The elements are, the name comes from these two conditions. So let's move on to the next page. Okay, so I would like to describe the space again, the space that we have seen, the stable space, as using gamma spaces. So remember that gamma spaces, they model connective spectra, and in our case, that will be the case. So we will obtain a spectrum whose associated infinite loop space is the classifying space that we have seen for the stable unitary group. So that will give us the generalized cohomology there. So let me spend some time here using this, introducing these gamma spaces. So we need another category, the category of finite pointed sets. So I use this notation, but actually I mean the skeleton of the category of finite pointed sets. So the objects here are denoted by K plus. So this is 1, numbers up to K, natural numbers up to K, together with an adjoint base point, disjoint. So this is essentially, there's a point here. So this means 1, K, disjoint union plus. So this is the base point, where K runs from all the natural numbers. And the morphisms, they are denoted by, we will denote them by alpha. So these are pointed set maps. Okay, so a gamma space is kind of similar to a simplicial set or a simplicial space. So it's a functor from this finite, from this category to pointed topological spaces.
Just to be clear, are you viewing 1 through K as an ordered set or just a set with no
just
additional
a set,
structure?
no additional structure. They are not ordered, so we have only pointed sets. Yes. Okay, so this is the gamma space, and here the remark is that normally, I mean, the name gamma comes from the category, which is the opposite of finite pointers. So this is how Siegel introduced these objects. So he essentially defined gamma, but the definition of gamma is more complicated than these finite pointed sets. Okay, so given a gamma space, this can be extended. So it's F can be extended to all pointed spaces. So essentially, we have we can construct a functor. So if you consider this inclusion of these pointed sets, regard them as a topological space, and you can extend F to top star, which we will still write F for this extended functor, and this functor on a pointed space is defined as using the Cohen formula. So it's the value of the functor at the K plus, and you take the K-fold product of X. So this is a Cohen formula. So this is quite similar to a geometric realization. So you have this operation here, which glues these pieces inside using the morphisms inside the category. The precise structure is not important for us. One thing is important, which is there is an assembly map from this space smash bit Y, where Y is another pointed space, to F of Y smash X, X smash Y. Okay, so this map is going to be important because if you, using this structure, you can introduce a spectrum associated to gamma space. So we will denote the associated spectrum by F of S. So that's a sequence of spaces where you evaluate this functor on spheres. The structure map of the spectrum is given by these assembly maps. Okay, so let's see the most important example for us. So you take the functor Ku, which will correspond to complex K theory, connective complex K theory. So this is a functor which is defined as follows. So K plus is mapped to a space. So let's first define the space as a set. So this is K tuple of finite dimensional subspaces of C infinity. So this is finite dimensional subspace. And these spaces are pairwise orthogonal for all ij. Well, we have to suitably topologize this. But before the topology, let me just define what the morphisms are. If you have a morphism alpha, like here, then this is going to take a K tuple of spaces to an L tuple of spaces, subspaces. So you take the direct sum over the pre-image of alpha at 1 up to, again, a direct sum pre-image at L. Okay, so this is how the functor is defined on the morphisms, and this thing is supposed to be suitably topologized. Well, I'm not going to define what the topology is, but it gives you an idea if you look at the topology. So let me write it here. So the topology is such that when you look at the space at 1 plus, this is the disjoint union of Grassmannians here. M Grassmannians inside C infinity as M goes over the natural number. So the topology is such that this holds. The higher ones are not important essentially, because when you take the spectrum and look at the associated infinite loop space, it will be a space that's obtained from this one. So in this case, it will be like the group completion of this.
What is alpha here?
Alpha is a morphism in the category.
Which category? Where?
Finite pointed sets. That's the
from where to where? The
K plus to L
finite
plus.
Sets to sets. Okay.
So Ku is our functor.
You're defining the morphisms as tuples.
In the example, I'm defining the functor Ku. An object is sent to this space, and the morphism is defined this way. So this is the definition. Okay, so if you look at the associated spectrum using this construction, you will get a connective spectrum corresponding to topological complex K theory. So let me just go to the next page. Okay, so now I want to describe another construction for a gamma space. If you take a pointed space and a gamma space F, we can construct another gamma space, which is F sub X, that takes K plus to the value of F at X match K plus. And the morphisms are defined, a morphism between K plus and L plus is mapped to a morphism between the smash products, and then you apply F to that. So this is essentially a functor on gamma spaces. Starting from a gamma space, you get another gamma space with respect to a fixed pointed topological space. Okay, so given these constructions, we can introduce the commutative d-torsion K theory. So let's first define this subgroup generated by 2 pi I d, so it's the d-torsion of unity inside U1. So this is a subgroup, finite subgroup. So this is essentially a notation. The spectrum corresponding to the gamma space Ku sub b mu d. So this is the classifying space. I'm applying this construction where x is equal to the classifying space of mu d. And you look at the spectrum of this gamma space is called the commutative d-torsion K theory spectrum. So we will write K mu d for this spectrum, and also for the corresponding generalized cohomology theory. Okay. Right. So let's see. The theorem that I want to talk about, and it will connect this construction back to the classifying space that we started with, is the following. So this is an idea due to Gritschacher and Hausmann, Simon Gritschacher. So let me try to spell it correctly. Okay, and Hausmann. So they looked at the case, the commutative case, and their construction, their idea also works for the Z mod D case. So that's what I looked at. So essentially, it's a modification of their proof. So K mu D is stably equivalent to Ku smash B mu D. So this is the first result. And if you look at the infinite loop space K mu D associated to K mu D, so this is weakly equivalent to the classifying space Z mod D U. Okay, so this is the connection. So in this theorem, we see in particular that this classifying space at the stable unitary group is an infinite loop space. So therefore, it represents this commutative d-torsion K theory. And here, this is going to have extra benefits, which will allow us to compute the homotopy groups. So let me just sketch the proof of this and tell you how this works. So essentially, the idea goes back to Siegel. There's a very nice paper of Siegel where he compares topological K theory and algebraic K theory. And the construction goes back to that particular paper, essentially. So we call that.
Yeah.
Yes.
This definition of the Ku spectrum. So you're using the definitions before that, f sub x. Is that what you mean by u sub some b mu d? So can you expand that definition a little bit more?
Okay. So I'm applying this construction to the gamma space Ku that we defined on the previous page, and I'm taking X to be the classifying space of mu D.
Classifying space of mu D.
Mu D is a group.
Just a cyclic group, right?
Yes.
So you're taking a classifying space cyclic group of order D, and F takes X.
And I'm looking at this gamma space F sub X constructed like this. Yes, compared to,
This is the commutative d-torsion K2.
Yes, and I'm looking at the associated spectrum, which is that one. So the associated spectrum is denoted like this, K mu D, and it's the spectrum that we are interested in the stalled commutative d-torsion K2, yes. Okay, so yeah.
It almost looks like you're heading for a trivial result then, I guess, right? I mean, you're defining the cyclic classifying space and maps spectrum defined using the cyclic classifying space. And then you're looking at the classifying space defined by cyclic, the torsion elements inside the U. Anyway. Okay, continue, thank you.
Okay, so recall that K mu D, as we just discussed as the, it's just right now, it's the spectrum associated to this gamma space. And this spectrum K mu B mu, Ku B mu D, it takes K plus to Ku applied B mu D smash K plus. Okay, so this is just a reminder. So we want to consider, so let's start by considering the space, the value of this gamma space at 1 plus. So that would be, by definition, smashing B mu D with 1 plus, which is just B mu D. Therefore, this would be just K U B mu D. Okay. And then the idea here is that what is inside is the geometric realization of a simplicial set, right? Given by this simplicial set, right? It's the n-fold product of mu D. The observation here is that the K mu, when you apply it to a space, is a co-limit construction. And this geometric realization is a co-limit construction as well. Therefore, you can commute it and then look at the geometric realization of the simplicial space given by this. So you look at the values by evaluating space by evaluating Ku at mu D to power n. So essentially, if you want to understand the first gamma space applied to 1 plus, you should, it suffices to understand what this is. Ku at mu D to power n. Okay, so this thing can be mapped to the level of n, the space of n simplices of the classifying space. So this is the n simplices of this thing. Okay. So this is a very natural map. It's quite a nice map. So if you have, so this is, remember, is a co-limit construction for where the pieces are given by these finite dimensional subspaces, and the lambda I are elements of mu n. Okay, and also to parameterize this n coordinates, so there's an n tuple of elements here, so I just use J here for the n tuple. So you send this to the pairwise commuting n tuple of unitary matrices, which are d-torsion, where AI acts on each VI by multiplication, sorry, Vj by multiplication by lambda ij, and acts trivially on the complement of this sum, okay, inside C infinity. So these are the matrices, and it turns out that this is a homeomorphism, and the inverse map is given by simultaneous diagonalization of these n tuple of commuting pairwise matrices. So this is something one has to verify, but this is a very nice map, and using this map, we see that the n simplices are identified like this. So to be able to finish the proof, one needs to use some properties of gamma spaces, which is kind of, after this observation, it's kind of automatic to see how things works. So essentially, using the previous observation, we have seen that this space, gamma space evaluated at 1D, is essentially going to be this. Okay. Just to finish the proof, one uses some properties of gamma spaces. So if F is a gamma space and it's very special, that's a technical condition, and then in this case, the factor evaluated at 1 plus is the infinite loop space associated to the spectrum. And the second case, second property that one uses is there is a natural map from the spectrum smash X to the this gamma space constructed from X and F, applied the spectrum corresponding to this gamma space is a stable equivalence. So this property B gives us the stable equivalence between K mu D and Ku smash B mu D. And the second, and the first one gives us gives the second statement, which is the infinite loop space is weakly equivalent to Z mod 2 du. So this is kind of the idea. Essentially, this observation is the one which relates the spectrum constructed from the gamma space with this classifying space Bz mod du. Okay. So let's see how this affects the homotopy groups of this space. So if you look at, so using this, we can compute the homotopy groups of this space. We can simply pass to the spectrum, because so this is homotopy groups of the space, and this is homotopy groups of the spectrum. And then from here, we can use the stable equivalence by and the isomorphism between the homotopy groups. So we can pass to this thing, K mu smash B mu D. But this is by definition is the Ku homology in degree R of the classifying space mu D. And these groups are computed, they're known. For example, you can look at, there's a book by Brunner and Grillness, which is the Connective K theory of classifying spaces of finite groups. So if you look at this space, then what happens is that, so when R is equal to 0, you have 0. When R is equal to 1, this is Z mod D. When R is equal to 2, this is 0, and so on. But I'm not interested in the higher ones. Just these three is going to be enough for our purposes in this talk. Okay, so this is the spectrum. So now I want to talk about the applications of this spectrum, but it seems like that I'm almost coming to the end. So, so what is the usual end time for the talks? Is it 1 hour or less than 1 hour? Like, am I supposed to finish at 2:30 or can I continue until 2:40?
You're the organizer. You can decide, I guess.
Okay, so what is the
usually 50 minutes, but we finish at 30 because people go to teach. Usually at 40. Okay. But today we don't have 40 classes, right? So you can go 1 hour if you want.
Okay,
but
so
normally, yeah, cycles is like 40 to 30. But today we don't have teaching, so.
Okay, and also there was some disruptions with the talk, so I think we lost maybe 5 minutes or 10 minutes just to set up the connection. Okay, so I'll just very quickly finish up by saying that how this thing can be applied. Okay, so I was hoping that I will come to this point much quicker. Okay, so how this works, I can only sketch the idea probably how this thing can be applied to something. Right, okay, so first of all, the classifying space that we have here, we can construct, so mainly for applications, we are interested in a fiber sequence like this. So we obtain from the classifying space of this stable unitary group, the n tuples here, you can act by the classifying space of B mu D. So essentially this thing acts on that level-wise. And then you can take the quotient of that to obtain another space, and it's essentially a fiber sequence. And the applications essentially depends on this space rather than this space. So the generalized cohomology theory that we obtained is corresponding to that one. But for applications, we need to introduce another generalized cohomology theory that is depending on this space here. Okay, so maybe I should first describe this before going into that. I should describe, yeah, so, okay, maybe it's not a good idea to rush this like this very quickly. Maybe I should even give a higher level of view of this. Okay, so maybe I should give a different way of, okay, so let me just back up and try to say things much quicker. So we had these pieces for each unitary group M by M matrices. So these are the pieces that are kind of hard to compute, but we were able to stabilize this space to something like this, which turned out to be corresponding to a generalized cohomology theory, and homotopy groups are easy to compute. So let's look at this, consider UD as a subspace, subgroup of UM, which sends the element to the diagonal matrix here. So I'll denote this by inclusion by delta M. So as I said, this acts on this space, and then you can take the quotient. So it's better to take the quotient in this before stabilizing. That's kind of the whole point. And as I said, this space is the one which is important for applications, but we cannot compute the homotopy groups of this without knowing the homotopy groups of this. Therefore, there must be a way to stabilize this. But the whole problem here is that the stabilization maps between UMs, which go like this from UM to UM plus 1, and so on to the stable unitary group, these maps, they don't descend to the quotient because of the definition. It doesn't commute, so you cannot really write commuting maps. And so you cannot really stabilize this space in the same way you stabilize this space. So therefore, the idea is, instead of taking quotient right here, you take a quotient in the stable category. So you replace this classifying space with a stable version, which would be the suspension spectrum of B mu D. And you can write a corresponding map for delta M if you consider these things as gamma spaces. There's a very natural map that you can write down. And then you look at the cofiber sequence. Sorry. Then you can look at the cofiber sequence in the stable homotopy category. And the cofiber is going to be a spectrum which I will call CDM. So D is the same D, and M is referring to this M here. So that is keeping track of these two numbers here. And this spectrum is the one which has applications. Okay, so after introducing this spectrum like this, one can ask what are the homotopy groups of this spectrum. So let me tell you in the next page. So
how do you keep track of M? M is like before the stabilization.
Yes, let me go back. Okay, so what I do, there is a map like this, delta M here, and there is a map here corresponding to this map. So the index M is going to be kept here. So let me just give you how this map is introduced if you think of these as gamma spaces. So that will be induced from the map of gamma spaces between, I didn't define this, but if you know what that means. So this is going to be determined where 1 plus goes. So you have this Grassmannian here, it's infinity. So I'm taking 1 to the subspace generated by this canonical basis. So this is Cm. Okay, so this M is kept here. So I'm taking, I'm using this gamma spaces and then applying this functor to pass to these gamma spaces with a subscript B mu D. and then you take the associated spectrum to obtain this map. So there's a couple of things. But the idea is that to write down a stable version of this thing, so therefore the M index carries over. Okay, so yeah, the spectrum. Then the spectrum turns out to have quite simple homotopy groups. So let me write them out. Okay.
How is the homotopy groups of the spectrum relates to the what you wanted to calculate at the beginning before stabilization on the the B bar?
Oh yeah.
How is it?
Okay.
Is there you lose that, or you know the connection between them?
So there is a this construction gives you a map. Comes with a map from this to the infinite loop space of that spectrum. So therefore, you can relate the homotopy groups, and you can say something. So essentially, we are interested in maps from a two-dimensional CW complex to this space, but these homotopy classes are hard to compute. So you just stabilize it using this map, this space, and then you look at the CDM cohomology of a space. And these are easy to compute.
Do you know if it's homotopy equals or anything about that map you wrote?
Here, you mean this map? No, no, we don't know anything. It's like this map. It's like this map. There's a map like this, but we don't know how to relate these two.
And how are you going to use the homotopy groups of the CDM if you get the homotopy groups? How are you going to get something about B bar?
So the goal is not to immediately get something about B bar. So in this talk, what I wanted to emphasize is that I look at this spectrum and I look at the homotopy classes, homotopy groups of the spectrum in a particular case. And it turns out the non-trivial generator comes from some construction that appears in physics.
Having a map will be enough for what you want.
At this point, yes, because I mean, if I want to look at these maps and if these things classify something physical, I can look at these maps to get a coarser classification. Okay.
Thanks.
Yes. So the theorem here is that the homotopy groups of this spectrum turns out to be very simple. So it falls into the exact sequence here. So there's this multiplication by M map by 1 CDM. So I'm just doing this very quickly. Sorry for being late. And it's kind of hard to estimate time when you talk on this screen. So I should have done this much quicker. So it turns out the CDM cohomology on a space splits canonically in an interesting way. So it gives you the first cohomology of X. Here we have Z mod D. So we have the pi 1, which is Z mod D times M Z mod D. It's the quotient group. Direct sum H2 of pi 2 here. So this kind of, here we have Z mod D, the M torsion elements here. That's the notation for the kernel. Okay. So after knowing this thing, the homotopy groups of this thing turns out to be very simple, and we compute this from the homotopy groups of K mu D. So remember, we know the low dimensional homotopy groups of this. Oh, by the way, when I define this, I'm not interested in higher homotopy groups. So the definition actually kills off the higher homotopy groups of degree greater than 2. So we are not interested in this because in applications, we want to apply it to. So let me just do very quickly just to connect. Look at the case where D is equal to 2 and M is equal to 2 square. So I want to understand C2 to 2 square. So this is the particular case that I wanted to look at a sphere. Okay. So if you look at this isomorphism, you will see that you have the first cohomology of a sphere. So this is 0. And the second cohomology of a sphere, and the M torsion elements in D, in this case, is just going to be Z mod 2. So you have Z mod 2 here. That's the second cohomology of S2 with coefficient Z mod 2. So there are two elements here, 0 and 1, and the description of the non-trivial element turns out to be an interesting construction. So, okay, in 2 minutes, I can explain the construction. So the construction goes as follows. So you take the torus first, and you define a map to first the unstable thing. Okay, and then the construction tells you there's a map to C222 infinite loop space of this spectrum. So this comes by construction, and the goal is to construct this map. And this map turns out to be something interesting. So you start from a torus, you triangulate the torus in a certain way. Okay. To be able to define this map, you essentially have to label these edges with unitary matrices in a certain way, right? The rules that you have to keep in mind is that each operator, each unitary matrix has to be squared to the identity matrix, and in each triangle, the matrices are supposed to pairwise commute. And the matrices which appear in this construction are the Pauli matrices. So you start from 2 by 2 matrices like this. So these are the Pauli matrices, and there's the Y. And using tensor powers of these things, like for example, in here you would take X tensor identity 2 by 2, and here you would take Z tensor identity 2 by 2, and then you would fill the rest similarly using tensor powers of these matrices. That would essentially define this map. So constructing this map is essentially labeling these edges. And this is known, so this construction is known as an operator solution to the linear constraint system determined by a linear equation. So I'm not going to define what a linear constraint system is, unfortunately, but it is related to these operator solutions of something. And these appear in quantum information theory. They are important. For example, I would like to refer you to a recent breakthrough by Slofstra. So he proved an embedding theorem, which is a purely group theoretic theorem that uses these kind of constructions, and then he solved the Cyrilson problem in a negative way. So it's the resolution of the Cyrilson problem. These kind of structures play a role in these problems, and that this problem, if you're familiar with this, it's essentially about a separation between different kinds of quantum correlation sets. So this is a fundamental problem in quantum theory. Anyways, so this construction is the combinatorial version of this construction. When you think of it as a linear constraint system, is known as Merman Square. And in our earlier work, we came up with this torus version. Anyway, so you construct this map, and it turns out, if you look at the composite, it turns out it's going to factor through S2. And then this map is the representative of the non-trivial element here, it turns out. Okay, so this is kind of the end. Sorry for rushing half of the talk, but I was not expecting to go that slow, given the pace on a blackboard that I usually have. Okay, thank you very much. Okay, is anyone still there?
We're still here.
Okay, so let me stop the